So at this point, we're going to try to remember the invariants of Paxos. Even we are now discussing sequence Paxos, but these invariants would be very instructive, and you can see how you're going to modify it to achieve the invariance for sequence Paxos. So this has been discussed before, but let me just quickly go through it. There was an invariant called P2C. What this invariant says, it says for any value of V and N, if a proposal with a value of V and the number N is issued, if this is issued, then we will always find a majority set, that is a core majority set, such that either this majority set did not accept anything, or this value V is the highest numbered proposal among all proposals numbered less than this number N, less than number N, that is accepted by acceptors in this majority set. This says that for a proposer to issue a value, this value should be either a new value if the acceptors did not accept any value, or it should be the value collected from a majority with the one with the highest proposal number. Now, this condition implies that if a value is chosen, it means there is a majority set for this value, then every higher proposal issued will have this value. This should be clear, because if the first condition is satisfied, then the proposer that issued V and N will pick the value with the highest number, and if that value is chosen, it means there is a majority for it. You will always pick it regardless of which quorum, which majority set you pick. You will find this value, and therefore you're going to issue it. Now, given that it's true that if a value is chosen, then every value issued by a proposer has the value V, and if a value is chosen, then every higher number proposal accepted by acceptors will have the value V. Remember that acceptors always accept proposal that higher, the highest proposal, as long as the promise that they have is valid. And from this we got in Paxos that if a value is chosen, there's a majority for this value, then every higher number proposal will again have the same value, and the value will be chosen. So this was the invariance of Paxos. Now let us see what would be the invariance here in multi-Paxos or sequence Paxos that we are defining. So observe that a quorum is a majority set, and here is our invariant, which say if a proposal with a sequence V and a number N is chosen, then there is a majority set of acceptors such that this sequence V is an extension of the sequence of the highest number proposer less than N accepted by any acceptor in this majority set. So what this is saying if a proposer issues a sequence, then this sequence is an extension of the sequence that with highest number proposal in accepted by acceptors. So let us see. If we look at this point, so C1 was issued, and this is completely correct because all the values less than n equal 1, the values of the sequences with a round number less n equal 1 were the NP sequence, so that is valid here. But what's going to happen here is that if we come to this point, so assume now that the proposer did not complete his operation because another proposer took over with a higher proposal number. And that one actually now issued C2, which is an extension of the sequence with the highest number less than n. This is quite okay. This happened because the proposer actually got contact with acceptors P2 and P3. So this was his majority set. If he would have got a response from these two, P1 and P3, he would have extended the sequence C1, but he didn't, which is fine. Now we have a chosen sequence, which is C2. So any quorum will have this sequence here. I think that is fine. So here we have a situation where at round 3, still we have C2. So what happened in round 3? Round 3, some other proposer came, and what did he do? He just picked this majority set and extended C2 with C3, and it happened here. He didn't manage to extend this slot because some other higher proposer came in. Now we have this situation where is another proposer came and extended the sequence by A, which is fine, but another one came and took over. And what the proposer came here and took over did, he actually saw this acceptor and this acceptor and extended the sequence, or saw this acceptor and this acceptor and extended the one with the highest number. That's why the proposals C2, C3, and CA did not get a majority, and therefore it was overwritten with another longer sequence, which has in the end B, D instead of A. So as we said here, so the highest number proposal accepted before round 4 was this. So it is okay to issue this after that, if you think to this description. Also, it is okay to issue this. So the algorithm maintains this invariant that is mentioned here. And this is done in the prepare phase. And it is done by reserving the acceptors, so not to accept a proposer less than n. So this is actually not difficult to understand. Here's the following situation. So if in the prepare phase a proposer came here and reserved these acceptors, so he actually got first C2 and C3 and then reserved them, then he prevented the proposer that wanted to extend the sequence by A. So this is the idea of promise. You have to satisfy this condition across rounds, and you do that by reserving the acceptors. And this was clear here. You can see it in the algorithm. When you send a prepare, and if your number is higher, then the acceptor will say, I promise I will not accept any value less than the number that you gave. And that's what happened here. The acceptor does not accept values less than the promise he promised before. So this is basically the algorithm. It's very simple. So an observation now, which we say is that any majority set contains the longest chosen sequence, as you can see here. This is the idea of a majority. So these two acceptors contain the sequence C2, which is the longest chosen sequence. Therefore, if a sequence V is issued in round n, then it will always be extension of all chosen sequence on a round less than n. So that it means that for this guy, whenever after the prepare phase, he extends the sequence with C3. So he will never miss the longest chosen sequence, let us say. Now we have everything in place now. So, and this you can check for yourself. In Paxos, we're talking about proposing a value, and if the value is chosen, then the issued value by a proposer is this value. In sequence Paxos, we say if a value is chosen, it is a sequence, then every higher proposer number is a longer sequence, so has v as a prefix. And this is guaranteed by the algorithm. And this leads us to the following, that if a sequence is chosen, then every higher proposal accepted by any acceptor has v as a prefix. And then, if a proposal is chosen, like this sequence is chosen, then every higher number proposal that is chosen, which means accepted by a majority of acceptors, will have v as a prefix. Given this, now we have a correctness proof of the safety properties of the sequence consensus. So just to mention now, C2, if a proposal is issued, it is an extension of the highest numbered proposal by an acceptor in a majority set. This implies that if a proposal is chosen, then every higher number proposal issued by any proposer has v as a prefix, and also then implies that if a proposal with sequence v is chosen, then every higher number proposal accepted by an acceptor has v as a prefix. And of course, if this implies that if a proposal with sequence v is chosen, then every higher number proposal chosen, and that if it's chosen, it will be decided upon, has v as a prefix. So P2, basically in a different way, says if u is chosen in round n, and v is chosen around n prime, and n is less than n prime, then u is a prefix of v. So u is the shorter sequence prefix, or equal, depends on you think about duplication or not. So that is great. Which would mean that if a proposer proposes a sequence, and then in a higher round he proposes another sequence, then that later sequence is a longer sequence than the previous sequence, and the previous sequence is a prefix. So if a sequence is decided, then it was before it is decided, it was chosen. And this is the same for u and v. So we have our properties now satisfied. For any two sequences that are decided, one is a prefix of the other. That is correct, because either n, the round number of n, is less than n prime, or n prime is less than n. So that satisfies agreement. Integrity says if a process decides u and later decides v, then we know that the length of v is longer than the length of u. Or u is a prefix of v. And the validity, which says only sequence of proposed commands are decided. In the validity case, from the promised response, a new command is appended to the chosen sequence v only if it was proposed, and this comes from a proposal. And therefore, every elements in decided sequence are elements that are proposed. This ends the correctness proof of sequence Paxos. We have a reasonably high confidence that this algorithm is correct. Now we are going to move from an algorithm which is quite inefficient by stepwise refinement of this algorithm, so that we get a very efficient algorithm. And that will be in the next unit.